Hello, everyone. I see some people slowly joining in. So thank you so much. Welcome to the Ambient Scientific webinar, Boot, Blink, and Believe. We have our core speaker here with us as well, Swapnil, and we will shortly introduce him as well. So while we get started, can some of you put something in the chat so we can see that the chat is active? Okay, great. Why don't we see where everyone is joining from? So if you can start putting the cities where you're from, we'll get a good sense of where everyone is joining in from. Okay, awesome. I see Thailand, Singapore, Netherlands. Okay, Bangalore, quite a nice diverse audience. So welcome everyone. So awesome. Okay, without much ado, let me share my screen. And I will give a very quick overview on who is Ambient Scientific, what do we do, and then we'll introduce the speaker as well and start the actual webinar content. So some of you may already know, but for those who are not aware, Ambient Scientific is a fabless semiconductor company, and we're actually extremely focused on building very high performance, yet at the same time, very low power programmable AI processors. As a company, we're based in Santa Clara, California, but we also have an office in India. And essentially, our goal or the key problem that we're trying to solve is the energy problem of AI compute. Some of you may know that AI compute today consumes a huge amount of energy, whether that's on the cloud side or on the edge side. And as a company, we're extremely focused on trying to solve that problem from the underlying root problem itself. And in order to do that, we actually went down to the metal layer, reinvented new kinds of circuits, created our own instruction set, and that gave rise to a very unique technology that we like to call DGAN. It's a play on two words, digital and analog. So essentially, by leveraging analog in-memory computing, we're able to deliver significant AI performance, power, and area benefits as well. And I won't go too much into these details, but we'll have a Q&A session at the end where if you have any questions about either what we do at Ambient Scientific, our products, or anything else that Swapnil will talk about, please feel free to ask us. With this technology, we've already started to launch products in the market, and our first product is GPX10, which is a battery-powered AI processor. So this is essentially the world's lowest power AI processor that is capable of delivering such a high amount of AI performance on such a low power that it sort of enables a new category in the market that we call coin cell AI. So imagine being able to run sophisticated AI algorithms like voice control, biosignal anomaly detection for health and wellness, vision-based Face ID, and a lot more on as little as a coin cell battery. But not just this product, our technology gives us a very scalable roadmap of processors, all the way from small edge devices to hyperscaler cloud server level chipsets and everything else in between. So we're already working on our next set of processors, which will be focused on drones, robotics, on-device LLMs for laptops, edge server boxes, and much more. So stay tuned on announcements for those. Now, before we start the webinar, I just want to test a very quick feature. So we have a bunch of polls here as well that we want to try out and see, if you can interact with us. So I'm going to launch one poll here, and if you can answer them, we'll see the quick update on this. So basically, the first poll that we launched is how many years of experience do you have in hardware engineering? Hopefully, all of you are able to access it. On the bottom panel, you should see that there's a polls button or tab. So if you can just input your answers for those, it'll help us understand the audience and your current starting point. Okay, I don't see any answers coming in, so maybe there's maybe a small technical glitch here, but we can get back to that later. Oh no, I do see people putting in some answers. Okay. So just the first question. Just the first question. We'll come back to the next one later. So far we see quite an even split. We see an equal amount of people who are very new to hardware engineering, some who've been in the space for 5 to 10 years, and some who are somewhere in the middle as well. That's good to know. So I think now we can transition it over to Swapnil after just one quick announcement is that we're giving out our development kit to a lucky winner as well. So please stay tuned till the end of the webinar, and whoever's there at the end from that pool will pick one lucky winner and give away one of our AI development kits to the winner. So please stay tuned till the end. I think with that, Swapnil, you can take it away now and give a quick introduction about yourself and begin the webinar presentation.
Hello everyone, can you hear me? Am I audible? Is my face looking good? All set?
Yes,
Okay.
all good.
So,
And one quick answer to the question. No, you're not supposed to answer all the questions right now. We can answer them. Swapnil will flash the questions and then you can start answering.
yes, sure. Yeah, so first of all, thank you, Saj, for setting this up. Okay. And thank you all of the participants who are joining this. Good morning, good evening, good afternoon. Okay. Thank you. My name is Swapnil, and I take care of the chip platform engineering as well as hardware engineering at Ambient Scientific. I have almost 22 plus years of experience in the various domains in the areas I mentioned. Okay, so that is my quick introduction, and we should start. Serge, can we share the screen and let me take the participants through?
Sure, go ahead, Swapnil. You can share your screen.
Okay, you want me to share?
Yes. Yeah.
Okay, let me. Okay. So we start from here and let me see if I can put this. Perfect. So we have around 35 to 40 minutes. And as Saharsh mentioned, you can type in your question and answer questions and wait for the answers by end of this. We will allocate some 10 to 15 minutes as we move at the end of the session. This session is basically about the green part, which is chip, boot, blink, and believe. But before we talk about it, I just wanted to ensure that we take the thread from the point where Saharsh has left. So Saharsh has just spoken about what we do, and in general, we will talk about the age deployment and AI use cases. Then I just wanted to touch upon some of the concepts which are, very heavyweight. We should have a separate webinar or podcast for them. But definitely, I will just, quickly take you through. So concepts of what happens, from the requirement to the previous first stage, what happens after the wafer, GDS2 file is generated to the packaged chip. In the meantime, what is happening? So all these two things are happening remotely, not at the fabless house. What is happening in terms of SDK, DVK, and miscellaneous firmware development and test software development? Okay, and then once the chip has arrived, you are all ready to test it. Okay, and remember, verification or testing never gets over ever. So what happens? How do you test? What are the different phases of chip testing before we call it? Okay, we are good to go for the mass volume production testing and high volume manufacturing checkout. And of course, we are talking about AI, edge CPU, or in general, what happens and what kind of applications we are developing. Okay, so these are some of the very key use cases of the edge scenarios. You always, you would already know that we have been using these edge AI CPUs for the healthcare case, when probably some kind of locket, some kind of shoe, some kind of wearable is being used in terms of with the different kind of sensors, vibration sensor, pressure sensor, sound sensor. Okay, in automotive, industrial and automotive also, we have various use cases like detection of sleep on our those small instruments which are kept on our cabin to ensure that we are not distracted while driving. Similarly, different kinds of variable which kind of probe our and our sleep pattern, probably uh, the mental status plus our walking steps and all those kinds of things, kind of uh, applications, as well as the industrial predictive maintenance kind of use cases. All this are possible because of some of the very generic engineering implementations of these AI use cases. Of course, we are not talking about the data science part of it, which is very fundamental and inherent to this whole solution scheme of things. But we are talking about something in terms of the hardware features and what all makes these tiny devices usable or useful for the edge deployment. So in general, all these devices are doing some kind of fusion. Okay, we have some kind of audio sensor, vision sensor, or motion sensors. We actually fuse these sensors for and use the data for the training, and as well as we put this as part of the deployment for inferencing on the edge. Okay, ultra low power is very important in all those edge scenarios, because we are not talking about the cloud. These are all tiny battery operated devices, and we wanted to ensure that low latency boot happens. They're all always on systems, and they're always available in terms of usability for the user. Okay. Yes, sir. I think this is a reminder for a poll.
Okay, so I think this one was already covered, so we can skip this one, Swapnil, and you can continue.
Sure. Okay. So what is the meaning of success in terms of edge AI scenarios? There are probably two metrics I just wanted to touch upon. One is the cloud versus edge AI, and the other one is a non-AI CPU versus a general compute CPU. So edge AI against cloud system is generally not forgiving. It has it does not have infinite power budget as part of cloud systems. Of course, this is all headless kind of operation. We do not see what is happening as part of the microcontroller, as part of the entire as we do not have displays or the console for the debugging. We do not have real-time logs or dashboards which we can actually view from the compute or data log point of view. Of course, we do not have much of a thermal headroom, and it's all very critical mission sensitive devices or application. Okay, so in general, the success in all these AI edge CPU is it has to boot reliably, it has to blink deterministically. When I say blink, basically it means the whatever operation, tiny operations, the fundamental operations have to always happen deterministically. Okay, the production variability in terms of corner lots, the corner dies, plus process corners, voltage variability of the silicon are all taken care in such a way by firmware or hardware of the system or the solution, so that you can escape. I mean, there is no opportunity for failure. And of course, all this should lead us to a robust product, a robust system, so that it can scale to thousands of deployed units. Uh, Eventually, it should run inference because it's an AI edge device deterministically, reliably, and infinitesimally. Okay, so this is the success for AI edge, very fundamental to the definition of the chip. In this talk, what we are going to talk about is basically what happens, and once the chip comes, how do we, what all we need to test in terms of the silicon bring up, how to ensure that bring up is done, how do we do the board checkout by way of little bit extended testing, and how do we reassure ourselves and our customers and all the engineering and design teams that the production readiness for this edge AI CPU is green signaled. Okay, so that is what I wanted to emphasize as part of this session. Quick recap. What are the AI chip development process before we say the chip has arrived in the lab? Okay, of course, AI chip is very, very complex. Whenever we get an opportunity, probably in other seminars, other conferences, and here and there, we have been talking about the ingredients of our hardware software. Okay, but in general, AI chip also has a very, very traditional design, basically chip specification to the GDS to 11 stages approach. We get some kind of chip specification, we do a design entry, we do a functional verification, of course synthesis, all this front end partitioning of chip, design for testability, floor planning, placement, routing, CTS, till the final verification is done. Okay, yes, there are some very, very specific NPU, GPU, or probably in-memory matrix compute, or some of the very, very unique analog or custom IPs, which are unique from case to case for the those kinds of chips. So those are all part of this flow. This flow is is very generic flow. As I just spoke, RTL functional verification, gate level timing verification, power intent verification like UPF, CPF, and the design for test verification, design for testability is all very important for any kind of general compute, memory chip, storage chip, network chip, or even an AI chip. Okay. Emulation or the FPGA validation is very important from the point of view that in terms of pre-silicon, you have always working on these EDA tools, okay, which do not give us confidence of seeing the chip or seeing the equivalent logic working on the hardware. So at least we wanted to have the sensors are working pre-silicon before the chip has actually come from the assembly house. So we not exactly on the same libraries of the PDK from the ASIC, but on FPGA we can ensure that functional RTL we are able to implement, and we can actually do prototyping by running equivalent application software, APIs, drivers. And we can see the pipelines are clear in terms of vision pipeline or audio pipeline, sensor fusion pipeline by connecting the real sensors. Okay, so this is very, very important step. This also ensures that in addition to the functional verification, pre-simulation, whatever, we are also validating the chip from the profiling, bottleneck optimization, bandwidth, those kinds of architectural, no micro architectural refinement. Software optimization is done, and we are close to the real hardware. This is all backend or physical design portion, from floor planning, partitioning, clock tree synthesis, of course, power planning, IR drop, till the placement routing, and finally timing closure and sign off. Multiple iterations, even in front end as well as in the back end, physical design happen. And finally, we get a GDS2, which is in general, an year, up to an year, task by the various functional team members. Once the GDS2 is generated by the pre-silicon team, it basically goes to the foundry. We have multiples of those foundries based on the PDK we are choosing, based on the technology we are deciding. Of course, their tooling, their algorithms, their various unique selling points are different, but in general, the flow is create mask, and then we create a wafer. In the fab, we have to ensure that the wafer has printed those dies correctly, and visual inspection plus electrical inspection happens by the probe card technology. And then we get these wafers shipped to the packaging house. We do a die saw, we do some kind of die attach and wire bonding. Final testing is done, and then we do pack, and then we ship out either to a test house, okay, or in particular case,
Okay, it seems like maybe some sort of a technical glitch or network error. Yeah, Swapnil should be back in a few seconds.
basically based on the substrate and the die, we basically create final package, put a laser marking on this, and the packing goes to the production high volume side, or in our case, probably for the to the lab. In the meantime, all these when activities are happening outside the fabulous design center, the design teams and verification teams basically are working with the software team with respect to the workload partitioning, creation of firmware, okay, creation of memory hierarchy, tuning it, profiling it, doing some kind of bare metal firmware, doing some kind of little more complex real-time operating system, tiny RTOS based sequences for those kinds of prototype applications. We are just waiting that not only the chip arrives and we can do some bring up with these test sequences, but also we should be able to, once these test sequences are passing, we can do some kind of use case based application. Plus, when the chip arrives, not only a driver, API, application development, and test programs are being written. Also, we are also working in parallel for the mini ugly board, or probably DVK development board, or evaluation board, or test boards, wherein with the socket these chips can be loaded, and we can run all those softwares or test softwares and firmware, so that we can identify if there are some failures in the lab, and do some activity for revising the firmware, or identify if there is some fix required. Okay, so this all things are happening in parallel while we are waiting for the chip arrival. Uh, some kind of task, like for debugging, boot firmware preparation, diagnostic and test scripts, regression scripts, smoke testing, automation and power sequencing, and of course some kind of test vector correlation is also happening, so that we can actually utilize the time which OSAT is working in terms of assembling those chips. These some of the tasks are very specific to a custom CPU or custom AI CPU. For example, developing a compiler toolchain, okay, developing compatibility and demo applications and debugging, plus AI toolchain for the quantizer, optimizer, model deployment, model training. Those kinds of things are also part of this queue in tasks. The chip is being assembled in the assembly house, and now the chip arrives, okay, in the fabulous design center in the lab. And now let us see what happens.
Okay, awesome. So it's now time for the next poll, and this is a slightly technical question for some, maybe, but it's totally okay if you just want to guess some answers. We can see what people think are usually the root causes here. So please go ahead and put in your answers now, and I will quickly show the results then. So I can see the
Okay.
answers coming in. Just one second, Swapnil, the answers are coming in, still coming in. Okay, so most people think that it's because of moisture and baking issues.
So we have a fairly technical uh, team joining us, Darsh. Happy to know
Okay,
this.
so that's the correct answer then.
Yes. Yeah.
Okay, awesome.
Okay. So one rule, or one very important part in the whole scheme of hardware, semiconductors, chip, or whatever software development, you already know, the verification never stops. Okay. And the same thing is also true in terms of the chip verification. Now, it's very important to understand when the chip comes, okay? So chip is basically like, I've tried to basically make a chip and compared with the human life, okay? So the chip is alive, is kind of proving that the chip has some life, is equivalent to the boot confirmation from the chip. All the resets, clocks are in place, the regulators are working, the routing of the CPU getting up, and all this the first proof of life is visible, is all about boot confirmation. Of course, once we get this boot, this is all sequential. We want to ensure that peripherals are working, the peripherals are talking to each other, the processor, fabric, and various internal custom IPs are also intact. They are able to basically bare metal or whatever way, or they are able to interact with the software. And this is what is basically about Blink, or the hello world of the semiconductor world. Okay. And once these things are done by way of course, some kind of design validation test or system level testing, or the test firmware, we have to ensure that the entire thing is rigorously tested, by writing some kind of mini applications, system level tests to prove that the chip is trustworthy. Okay, this is what we call as belief. So, based on these three hypotheses in sequence, we will be, taking you through the various stages of this whole and emphasize the ingredients of boot, blink, and belief. Okay, so once the chip arrives, basically we do some kind of initial headless. There is no panel, there is no display, and we just wanted to ensure the test firmware is loaded into an external flash or external storage or wherever, and the ROM code is something which is being allowed to get alive and does its first operation. So we ensure that ROM code is basically able to fetch our first test program, and we can do a deterministic ROM load, fetch the integrity, power interruption tolerance, boot time, is calculated, ensure that SRAM banks are working, the load from the flash is working, all the internal regulators, reset controllers, the clock tree, and the reset tree is nicely propagated as per our understanding of our uh, and we have already tested this on the pre-silicon. The stability, the clocking architecture, the PLL versus LPO versus DLL or whatever is there, the distribution of this against the voltage corners, against the temperature corner, and against this corner in a nutshell also is tested. The entire power tree, power sequence is complied, ensuring that this whole thing is a repeatable behavior. And of course, this whole thing is basically tested with a different kind of test firmware, which is for a tiny AI CPU kind of devices or SoCs, is loaded into a flash. Okay. Now, while whole thing is done via ROM, we once this is working, we allow JTAG access and test the JTAG access or SWD access or whatever. So JTAG or SWD is small port which basically gives the control over CPU from the background so that a software can load. Okay, and then we can actually run more complex software. So JTAG allows us to run the software directly from the SRAMs, while the ROM is a real scenario in which we ensure that the software is loaded from the flash to the SRAM and execution happens from there. So once the JTAG or SWD or whatever debug mode works, it opens a plethora of methods to actually start testing the chip. Okay. Yes.
Okay, and it's time for the next poll. So feel free to start putting your answers in. So why does the system boot fine but resets when peripherals are enabled? And we'll give chat some time to put in the answers. So I can see lots of answers coming in, but two options are kind of neck and neck. Okay, so right now the answer that seems to be winning is interrupt from starving watchdog.
Absolutely right.
Wow, we definitely do seem to have quite a technical audience. Okay. And now that it's nearly halftime, a little more than halftime, just a quick check for everyone in terms of any burning questions the chat has, any acronyms maybe you didn't understand, anything that you would really like to clarify right now. We'll just wait for a minute so that those who are attending it put their questions in chat, and if not, then we'll continue.
Okay, so 39 people have answered this. This is really
Yes.
good number.
Yeah.
Very good. We are also getting some questions in the Q&A
Okay, let
section.
me see. No, nothing yet. So yeah, actually,
Okay.
yeah, if you have any questions that you would like to submit, you can also go into the Q&A section at the bottom and keep adding all your questions that other people can upvote as well, so that we have a list that we can answer towards the end. And one question is, will we be providing the PPTs? And yes, we will be sharing the presentation. It's actually already uploaded here. It's currently locked. As soon as we get towards the end, we'll unlock it and all of you will be able to download it. I think, Swapnil, someone is asking what GDS2 stands for.
Okay. So GDS2 is a very traditional name of a graphical design, kind of image it is. So you consider this as a stencil. I don't know how many of you would know the term stencil. So stencil or the negative print image of a camera. When this camera used to be not the current technology one, the digital ones. So we used to have those negative or stencil kind of thing. Once we get this GDS2, basically we can actually print as many uh, chips as we want. This whole GDS2 or graphical image actually is going to foundry, and they get this as an input by a very, very sophisticated heavyweight machinery like lithography, UV, and other tooling. And they can actually create a wafer. Okay, wafer will have multiples of those tiny dies. So die is considered, consider die as a imprint of GDS2. So that is what this graphical design schematic or image is the meaning of GDS.
Okay. And I see, Swapnil, that lots of interesting questions are coming in. So we love it. Please keep adding more and more questions. Maybe we'll answer just one more before we continue and we get to the rest at the end. So one question in chat, Swapnil, is how long did it take Ambient to develop the GPX10 chip from scratch and bring it to market?
Yeah, so we would not like, we would probably not talk about how much time it took to took for ambient chip to get into the life. But in general, we can talk about a chip takes around 9 months to 10 months. Okay, so it is very famous, kind of protocol or a story or saying that human life, the life of cow and the life of chip, okay, is kind of same. It takes 8 to 10 months, 8 to 12 months of time from the concept or the spec development to the GDS2 creation. And of course, there is its own sweet time taken by the OSAT, before that the foundries, around 2 months to 3 months, and another 2 to 3 months for the assembly. Whole of this thing can be, expedited. Okay, but in general, the cycle time for spec till the GDS2, considering all this design, pre-silicon, post-silicon, pre-silicon plus front end, back end, is 9 to 12 months. And put across 3 to 5 months of time for the assembly, post wafer to assembly of these chips. And as I said, verification never gets over. We have to test them, and there can be some revisions. Okay, and there will be some testing which will take another 1 month to 2 month time before we call it is production ready. Plus, if this chip is actually going to some kind of automotive or consumer or those kinds of things, there is a lead time of around 4 to 8 months for the qualification, a JEDEC based qualification. So that is what this is. 9 to 10 months, 4 months plus another 6 months. Did I answer?
I think yes, you did. And I think in the interest of time, maybe we keep going and we revisit the question and the
Yes,
rest of the questions
sure,
at the end.
absolutely. Okay, so we just did our boot. Let us do the blink. Okay, so blink is actually similar to the hello world, what we do in the software scenario, right? So instead of hello world display via AI CPU, we ensure we do the basic, operation of, okay, just glowing an LED, which itself is testimony that the boot, not only boot is working, the peripheral is working, the address map is working, the power plus the entire design is working, the firmware has been able to respond properly, and things like that. So all this rail, voltage accuracy, ripple noise, clock amplitude jitter, reset signals, power measurement during the blink will be confirmed. We do next phase little bit, getting more confidence in terms of toggling various GPIOs, seeing how much the latency it takes, then actually doing the hello world messaging on the UART console, receive something from UART, display something on the terminal, etc., etc. Peripherals like I2S, I2C, probably, and SPI, loopback, scan, and memory test, internal memory is all taken care. When I say internal memory, basically it's all registers or some kind of embedded flash or some kind of internal flash, internal memory, SRAMs. Those are tested. Little bit moving forward, the system enablement. So moving beyond from the bare metal code, we start working on the RTOS. Okay, can our firmware load an RTOS? And we can connect the external devices like SPI, UART, in terms of small, tiny environment. Okay, whatever interfaces it has, is our timer working? Is Watchdog, working? Are we able to get the correct interrupts on time? And the latency, bandwidth, profiling is all taken care. Of course, uh, connect camera. If there is a camera interface, connect an audio. If there is an PDA, PWM, or probably I2S kind of interface, do some kind of SPI, flash, read, write, SPI or I2C sensor, communication. All this is part of our system enablement. In addition to the AI accelerator enumeration, run some small code which ensures that the mag block is working, the neural network can be loaded, deployed, and some basic operations are also tested from the deep learning point of view. Then minimum firmware is basically extended to the extent of ensuring that can we actually test our DMA, do the interrupt latency, as I said, thermal throttling can be done, coherency, some kind of little extended measurement for power is also performed. The throughput profiling is done, and synthetic workloads. So all these are in a sequential kind of testing from phase 1 to phase 4, and this gives us a gradual incremental confidence in terms of confirming that the chip is in control and the reality check is done.
Okay, so this poll has also been launched now. And let's see the answers coming in. So the board powers up fine, but there's no UART output and no LED blink. What is the most likely cause? I see the answers
Think
coming
twice
in.
before answering.
Okay, okay. So Swapnil, I think, is trying to imply that this might be trickier than you think, but I am a little more confident that our extremely technically competent audience will still get this right. So this time the answers are a lot more spread out across all the options than all the other previous questions. Just
Yes.
10 more seconds till I close the poll. Okay,
So can they
so
change the answer?
nope, they cannot change the answer.
So
The results
remember
are
the,
in,
yeah.
and you can see the
So the
most
boot
picked
ROM is
answer
not
is
corrupt.
boot mode straps are incorrect.
Okay, good. That is the right one.
That's the correct answer. Okay. But the second most, the
Yes, yes.
closest answer was flash is empty as well. So maybe you can help them understand why that is not the correct answer because that's nearly uh, as likely put as boot mode straps are incorrect.
Yeah, so the board is powered up fine. And we have already said that the boot is happening. So boot ROM, the flash, and all this is fine. The CPU core is also working because we are able to boot. So of course, the very next thing which confirms, which decides the destiny of the chip is the strap pin post boot. So boot, I mean, in general, in most of the cases, the boot ROM actually, there will be a decision tree which tells that what to be done next, and that is mostly decided by the strap or the chip IDs or such technologies. So of course, post boot, which is confirmed by the flash, is not empty, CPU core is working, and the boot ROM is already working. Is the next immediate thing, which is the straps are not correct.
Awesome.
Okay.
So I think we may be
So
running a
now,
little bit behind on time, but that's okay. We can extend for a few more minutes after our designated end time as well. Those who cannot stay that long, please do not worry. We will email you the presentation as well. And those who can stay, please try to stay because we will announce the lucky winner for our development kit.
so lucky winner will be announced in this session itself, sir.
Yes, yes.
Okay. So let me uh, go through quickly. This is about Blink. Blink is, basically we are doing some kind of critical silicon validation. As I said, we just moved from bare metal to RTOS in one of the phase 1 to phase 4, which I explained earlier. And then, of course, we ensure that the risk mitigation, and reliability window is open. We just call this entire thing as design validation testing. Okay, which basically bridges us from the simulation to silicon. So pre-silicon has some kind of testing already done. We kind of borrow those patterns, those sequences beyond boot, plus adding those kinds of functional feature-based testing, and then ensure that reliable post-silicon validation is done. So while this DVT is happening, there is another little advanced term which we call, and that is called as system level testing. So in this, what we do is from the bare metal to RTOS, we start writing our own SOC based layers like HAL layer, API layer, driver layer, and we, based on the kernel and real-time operating system, and we write our own test cases. The same kind of layers is, once tested, we start using for our development of applications, which to some extent we have already tested in terms of pre-silicon emulation or validation. So this is the start for our performance optimization, workload characterization, of course, thermal management, and things like that. I think this is the last poll
Second
before.
last poll, actually, and quite simple. So again, we'll give our audience a few seconds. I see the answer is rolling in already. I think this was a little too easy. And I can see that there's one clear winner answer here. So I will end the poll and share the results. Okay.
Okay. Perfect. The answer is wrong.
Oh, really?
So basically, yes, yes. So basically,
Okay.
what happens? We blink, we behave, and yeah, verify the chip. Actually, we unless we have confidence or we have trust, and trust comes from the verification. Okay, of course, and verification comes from the observation and repeatability. So all are, in general correct in different scenarios, but mostly the final answer is actually trust. How do you get a trust? Trust is coming from verification. Trust comes from the repeatability. So the answer is trust.
Okay, so
So
this
it's
was
very
the
subjective.
trick question then.
Yes.
Okay.
Okay. Now let us go to the belief part that the chip is working as we expected, but we have not reliably done the full functional coverage, full application testing of the chip, which is the trust or the belief part. Okay, so system level trust is very, very important. Okay, because the system behavior is bounded. We already know the failure modes. We know how reliable the chip has to be. It has to be consistent. It has to be repeatable in any kind of environment, whether it is a moist environment, whether it's a very high temperature environment, whether it is a low temperature environment. It should work. The yield has to be very predictable. Okay, there are various variations in terms of the wafer, the chip, the die, the room temperature, the humid conditions, plus the process corners, plus voltage. All this comes from the physics or physical properties of the semiconductor. Okay, and this is very, very important step that we get this yield predictable plus reliability and consistent behavior of the chip. Sometimes the same kind of firmware does not work on one chip, but it works on the other. So we have to ensure that the software is tuned so that it works on all small minor variations which are happening from the physical property of the semiconductor or silicon. Okay, this gives us a real world operational confidence and ensures that we are ready for the field deployment. Now, this trust is basically very important. And how do we get this trust? So there are various different tricks. Basically, we ensure that with the PBT characterization, so process variation, we do multiples of such chips of the different process corners and test them against whether the voltage scaling conditions, temperature sensitivity or temperature scaling conditions, and of course run the various different kind of applications. All these 1, 2, 3, 4 parts are exercised in various different maybe chambers, with different kind of conditions. Okay, so this is our process voltage temperature variation PVT testing. Then we also have a very rigorous testing, which is called as qualification reliability. This is coming from some kind of JEDAC algorithm, and there is a mathematical formula which leads us to say that okay, if we run certain kind of test patterns with certain kind of conditions, then this is equivalent to the lifetime calculation or the mean time between failure of these chips, or it can sustain this much you know endurance quotient or the reliability quotient of the chip. So all these are very important from the chip point of view, because if you want to say the chip will be surviving in certain conditions for almost 15 to 20 years, then what happens is it is no way we can test this for 15 to 20 years in lab condition. So we have to accelerate. So all these reliability and qualification related test cases are the accelerated testing, which are done in the lab environments. Uh, Last but not the least, customer has some use cases, and it's very important that our hardware and software are interworking to comply to those kinds of customer use cases. Okay, we call this as compliance testing. There are some very default generic industry and regulatory certifications like ESD, EMI, EMC for the industrial safety, and of course some each and every geography can have their own compliance. We ensure that all these customer specific and industry and regulatory certifications are also met, and this leads us to basically final readiness for the mass production. Okay. While we are doing all this chip qualification, regulatory certification, we are also ensuring that we are creating some kind of demonstrations, some kind of demos, prototype applications for the customer-centric IoT operations or consumer operations, and give nice kind of messaging in terms of all this which is for the profiling, optimization, and as Harsh mentioned in some of the earlier slides, that okay, power or IOPS plus those kinds of calculations are met, and we can broadcast them. So all these workload partitioning, performance, energy benefits are proven by some kind of visual demos and applications, is all part of this EAI CPU kind of application development. This
Okay,
is the
so
last.
time for this is this is actually the last poll. So I've now launched it. And at the same time, we're now also open for any Q&A. So I already see some questions that are added in the Q&A section in chat, but absolutely anything you would like to ask us about our current products, future upcoming products, applications, use cases, underlying technology, we're more than happy to answer. And at the very end, we'll announce the lucky winner for the development kit, as well as upload this presentation that you were just going through in chat. Yeah, and I think our chat got this one right, which is
Absolutely correct.
basically, yeah, system has to be predictable everywhere. So I think I'll jump to the questions really quickly. From the question, oh, there's still some more slides to go.
Yeah, so I just will conclude with what we all discussed. I just emphasize on the green part here. Basically, what we did is it's very important that in general these things are not discussed, or these are not much discussed. Basically, I wanted to ensure that we talk about it and create some kind of awareness in the attendees and public. Basically, bring up DVT, SLT, and PVT, fall reliability. All these are different dimensions. which establish the reliability or the confidence for us to release the chip for the production. Okay? And this complies to our boot, blink, and belief philosophy. We are ready to ship.
Awesome.
Once we
Thank
are
you.
done, blink and
Awesome. Thank you,
yes, go
Swapnil,
ahead.
for such a lovely presentation. I hope everyone enjoyed that as well. And we'll try to answer as many questions as we can in a short amount of time. So, starting with some questions in chat, one of the questions is if Edge AI chip cannot be updated via cloud, how would that work with IoT devices? Like, let's say a heart rate tracker, where back and forth communication from the field to the home base is so vital to ensure that the user is healthy.
Yeah, so this is basically called as field firmware upgrade or over the air or probably wired firmware upgrade. There are various different methods of upgrading the firmware. In general, yes, revising the firmware is very, very important because you may want to add more interesting capability. Hardware cannot be changed, but we can actually revision up the software or firmware. So not necessarily we need to go to the cloud, but there can be a provision on the chip solution or the board, okay, where there can be some kind of simple Bluetooth or a UART terminal or GPIO device, GPIO slot, wherein we can actually just connect wired uh, host and load the entire firmware. You can also change those firmware by way of desoldering or making use of different kind of flash where the firmware is stored, or you can have some kind of BLE or small NB-IoT kind of modules wherein we can actually use some kind of mobile applications to load the firmware. So this all is part of the over the air or the wired or field firmware upgrade. And then for sure there are a lot of different considerations for it. So you don't need to always go to the cloud. It can be a different kind of strategy for the edge AI CPU firmware upload.
Okay. So the next question is, how can we reliably confirm that the chip is undergoing a proper reset and that all subsystems are reinitialized correctly after the reset event?
Okay, so reset is basically, we can have soft reset or hard reset. There are different conditions for the reset, warm or cold. So basically, we just want to ensure that those conditions are emulated for the chip when it's connected to various different peripheral, and we ensure that a self testing firmware is running as soon as the chip is reset and that self test firmware is booted via ROM code. That is what our first phase, which we call as a boot phase, was there. The self test firmware from the flash is loaded onto SRAM, and then it does some kind of operations like writing to some of the register files, reading the register files, ensuring that loopback from the UART or SPI or I2C is taken care. Internal memories are tested. So these are the basic test firmware, which is run as part of various different dimensions of the reset mechanism, and that gives us confidence that reset handling is working correctly.
Okay. The next question is actually very simple. I can address that with a very quick answer as well. So, is the DGAN system only capable of running AI models, or can it be extended to doing other math like matrix operations or so? So, this is a very good question. And actually, because our DGAN AI cores are vector matrix multiplication circuits, they can, of course, be used for all kinds of matrix operations, DSP functions for FFTs, DFFTs, and so on. So yes, they can be used for matrix operations as well. Okay, then just two more questions, two last questions, and then we'll get towards the end. Is where do you draw the boundary between bootloader responsibilities and application firmware responsibilities in AI SOCs?
So the bootloader is very fundamental to the any kind of operation. Uh, it is, I mean, in the beginning, as we said, like cloud-based systems and the edge-based systems. The difference, main difference also, is the way uh, the edge-based system has to be not only always on, but they have to be boot multiple times because we have to consume less power. Okay, so in general, this there is a trick that we put the entire chip on a very low power mode, or most of the circuit, most of the IPs, critical IPs are actually switched off, and when it and only allow degen in our case, or matrix compute or NPU, those kinds of AI part of it, to just be always on to sense the data coming from the sensor and do the inferencing. Now, if this is the case, which is traditionally always indeed is the scenario for the AI edge chip, then most of the logic, which is low power, which is in the sleep or deep sleep mode, has to be awakened. So when it has to be awakened, it is basically a boot from the maintenance CPU point of view. Okay? So that is what fundamentally boot is all about, which will always happen. The firmware, overall firmware, is a secondary portion of it. Of course, it is in general 10 to 20 times bigger than the boot image, and it will be actually taking care of the rest of the application, or which will make the uh, advanced operations beyond AI engine working for the always on mode, and maintenance, serviceability, sending some data, log the data, send to the cloud, get the messaging, firmware update. Those kinds of things are taken care as part of the extended firmware image or application plus.
Okay, so I think in the interest of time, we'll end the Q&A session here. And as promised, we've uploaded the presentation that Swapnil went over in chat as well, so everyone can feel free to download that as well. Actually, I think it needs to be uploaded to everyone, and we're doing that shortly. And now it's time to announce the lucky winner for the development kit as well. So we're going to run a quick algorithm across our participant list. And we see that the lucky winner is Neha Haripuram. So congratulations, Neha. We have your contact information. We will reach out to you after the webinar and we'll arrange for the development kit to be sent to you, with which you can prototype all kinds of exciting low power AI applications as well. And we just like to end by saying that, thank you everyone for coming here, listening to us, and helping us create a community where we're able to share this knowledge with everyone across various different elements of, the semiconductor life cycle as well. And we'd love to hear from you, what would be interesting for you for our next webinar session. It could be anything across embedded, AI, ML, hardware, edge boards. So please share some feedback with us, what you liked about this webinar, what you would like to see next time. And, until then, we'll see you next time.
Thank you, everyone. Thank you, sir, and all those who attended. Thank you so much.
Okay, we see a lot of good
Bye.
reactions coming in, but thank you. Thank you, everyone.